we ready again? So my last slides here gives more theoretical insight into the integral equation, telling us a bit about what's going on here. And this is very important insight. We'll return to that once we get to the numerical computations. We'll see that in the world of linear algebra, or matrix computations, we have something called the singular value decomposition. And I'm sure some of you are already familiar with that. But that originates actually in the singular value expansion, which is a tool developed for analysis of these integral equations here. So that's what we are going to go through here. And this is kind of a, I should say, lightweight way of doing functional analysis. I don't do all the really tricky and interesting parts. You see, I'll just write an equation there. In the top equation, I write equality, and then there's an infinite sum without really delving into what do I mean by equality there. Do I mean pointwise convergence, or whatever do I mean? So this is lighthearted because I just want to give you a flavor of what this singular value decomposition is about. So don't worry too much about these infinite sums and the equality signs and so on and so forth. I just want you to get the idea. And the basic idea is to write the kernel function there, a function of two variables, as a sum of functions, a product of functions u and v that depend only on s and t, respectively. So in mathematical physics, you might say that we are separating the variables here. Now, this is very, very convenient. And of course, in order to always be able to do that, you need an infinite sum. Otherwise, you certainly cannot do that. Okay? And then there are some scalars, mu. Right? Okay, so let's see. What more can we say? These, the u functions and the v functions, respectively, are orthonormal. Right? And since they have been normalized, we need those scalars, the mu I. And we can always order these components there in the sum in such a way that the mu's form a non-increasing sequence there of positive numbers. Right. So those are the fundamental definitions there. And then there's a fundamental relation between the u and the v functions. Now that's a very cool relation, actually, this fundamental relation. So you see what happens if you take your function vi, you take the ith of the v functions, you plug it in and you integrate with k, then out comes the corresponding u function, ui of s, multiplied with that corresponding mu there. Right. So there's a very simple mapping between the u's and the v's. It looks a little bit, it might look a little bit like eigenvalues and eigenfunctions, but this is more general here because we map from v to u. Okay. But anyway. Yeah. Let's see. The mu's, the scalars there are called the singular values, and the functions u and v are called the singular functions, of course. I have no clue why these values are called singular values. It's not just me. Nobody really knows. At some time in the literature, you'll see that people suddenly started to call them singular values if you trace back the literature, like a long time back. Nobody really knows why they're called singular, because it has nothing to do with the singular matrix. But singular also means something special, something unique, so maybe that's why. I have no idea. Anyway, just live with that. Okay. The interesting thing here is that we can actually write down now, for the first time, somehow an expression for the solution to our integral equation. You know, we've been writing up the Fredholm integral equation several times. This is the first time I actually give you an expression for the solution that you see there at the bottom. And of course, it's one of those mathematical expressions that it may not be so useful for numerical computations. Maybe not, but at least there is an equation there, and we can look at that and get a lot of information about the solution and how it's related to the right-hand side and how it's related to the kernel through the singular values and the singular functions. All right. So I'm not going to derive that expression there, just give you a hint of how it's done. See what you can do, since the v functions actually form an orthonormal basis for the space you're working in. So therefore you can write your function f in terms of that orthonormal basis, right? And since it's an orthonormal basis, the coefficients in that expansions are the inner products between the function and the basis functions. You can do that for your unknown function f. You can also do it for your known function g on the right-hand side. There you have to expand in terms of the u functions, because g is a function of s, right? So you do that. And again, the coefficients in that orthonormal basis are these inner products. And then you can plug that into the machinery, and after a little while you will end up with that expression there at the bottom. So it's an infinite sum, and it's of course we expand the solution in terms of the v functions, and then the coefficients are the coefficients to the g function divided by the singular values. Okay. So in order to better understand what that important relation there at the bottom is telling us, we would like to know more about the ingredients of that expression there. All right. So of course we know already that g is our right-hand side, but what about the mu's and the u's and the v's? Can we say something about those? It would be nice to know, because then we can say more. Right. Okay. So what can we say about the singular values? Of course, we have already told you that we order them so they are non-increasing. Right. It's a nice ordering. It's nice to have them that way. It turns out that actually the norm, the squared norm of the kernel, defined in that way there, is the sum of the singular values. Now, if your function k there is a reasonable function, it's not too crazy, then its norm on a finite interval is typically a finite number, right? Okay. So if the norm is a finite number, that means that infinite sum of the squared mu's must be meaningful. It must actually, this sum must converge to something that is not infinite. Right? This must be a finite number. And the only way for that to happen is if that the singular values must decay fast enough. Otherwise, that sum there will be infinite. So that actually puts a constraint on the singular values. So asymptotically, they should behave at least as fast as you see right there. Otherwise, that equation up there does not make sense. All right. So already now we can say something about the decay. And so what about q? Can we actually say a bit more about that number q there that defines how fast the singular values they decay? Well, there's a bit of theory along that direction there, and the theory says that if k has derivatives of order 1, 2, 3, blah, 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 until q, if those derivatives exist and are continuous, then we will have that decay there of the singular values. Okay, so q is somehow related to how smooth the function k is as measured by the number of continuous derivatives. All right. So in fact, a little while ago, we looked at two test problems there. There was the second derivative, and there was the 1D image reconstruction problem. I will just back up to the 1D image reconstruction problem. That was the one where we sent, where was it? There. Light through a slit. And the function there is a nice, smooth, infinitely many, it's very differentiable, right? All right. So it looked, the kernel K looks nice and smooth, and damn it, since it's infinitely many times differentiable, we have exponential decay of the singular values. It turns out that that's actually bad. Okay, that means that these problems, they are very, very sensitive to perturbations of the right-hand side. So why is that? Well, basically, you see here in the equation at the bottom for f that we divide with the singular values. And you know, division by small numbers is always a problem in practice. And of course, as the singular values decay really, really fast to zero, then we're in some trouble, because then we have loads and loads of small singular values. So for the 1D reconstruction problem there, with the smooth kernel, we have this very, very fast decay of the singular values. And so, boy, that is what we call severely ill-posed. That problem is severely ill-posed. The second derivative, on the other hand, maybe you remember that. That one, that was right there. That was the one that wasn't even differentiable across the line t equals s. It turns out that that problem is actually easier to solve, because here we have a singular values decaying like they are I to the minus 2, so it's only moderately ill-posed. So that's a problem that's easier to solve. This is very contrary to what you might be used to in connection with differential equations, because there you certainly don't like discontinuities. But here we like that kind of kernels, actually. So in fact, this is interesting, because we can relate the difficulty of the problem to something that in principle we can compute, and that is the singular values. Now, of course, given an arbitrary problem, it would probably be very easy not very easy. It would be quite difficult to sit down and write what are these u's and v's, but you can compute them numerically. Okay, and we'll see that next time. And then, of course, you can get a lot of insight about this. And here's one example of how you can do this analysis here by means of the singular value expansion. And this looks very much like one of the exercises you're going to do. But anyway, for this particular kernel, so what's the kernel here? The kernel is s plus 2t, right? This is a very, very special kernel that only has two non-zero singular values. The rest of them are zero. So that's called a degenerate kernel. And I give you here what are the first two singular functions, u and v. And then the claim is that we only have a solution. This is about existence then. See, that was one of the Hadamard conditions. What can we say about existence? Well, a solution exists only if the right-hand side is within the range of k, right? Because from that expansion of the right-hand side, you can see that the only two functions that can contribute to the right-hand side can be u1 and u2. So you cannot come with an arbitrary g. It has to have that particular form there. Anyway, one of the exercises you're going to do today is actually derive that result. So let's skip ahead. Because I also want to say something about the singular functions. All right. So we should remember that the singular values decay, and we can say something about the decay. The singular functions have a very characteristic behavior that I try to illustrate here for a particular problem. So as the index I increases, these functions tend to have more and more oscillations. It looks a bit like a spectral basis, right? Like sines or cosines. But these are certainly not sines or cosines. They are much more complex, much more complicated. But they still have that feature that as you increase the index I, you see more and more oscillations or zero crossings or whatever, how you want to characterize that. They seem to be more and more high frequent. You can see that from the picture there. Right? So this is an illustration of that fact. So to some extent, this can be proved that for many of the problems you encounter in practice, that the u's and the v's have this oscillation property there, that the higher index, the more high frequent they are. Right? And now remember that when we plug in the function vi to the integral equation, if we evaluate the integral, then we get mu I times ui. Okay. And the mu's, the singular values, they decay because we ordered them like that, because we found that convenient. So what this tells us is that the higher frequencies in the singular functions, the more damping. This is a manifestation, really, of this Riemann-Lebesgue lemma that we talked about before. The Riemann-Lebesgue lemma that ought to be a theorem, but isn't. Right. Certainly, higher frequencies are more damped. Let me back up here. Again, here we have the expression. Again, look at the equation at the bottom. See, we divide by singular values that get smaller and smaller, and at the same time the corresponding v functions here get more and more high frequent. So you see higher frequencies are divided by smaller and smaller numbers, so in fact they are amplified more and more. Precisely as we would expect from the Riemann-Lebesgue lemma. So this is very important to remember, that we have this spectral property of the singular functions, and we're going to return to that many times. This particular behavior. Anyway, all this insight leads to a fundamental condition here called the Picard condition. So this is a condition, of course, in the world of the singular value expansion. So this deals with the behavior of functions. And we'll see later that we have a corresponding discrete Picard condition actually in the world of matrices and vectors. We'll get to that. But I wanted you to see that this particular condition actually comes from the problem itself. It comes from the singular value expansion associated with the kernel of the integral equation. So anyway, if we want a solution f, okay, whose norm exists, whose norm is not infinite, why do we want that? Well, typically, if you put something in a machine and you measure it, you know that's what's inside there is not infinite. It doesn't have infinite mass or infinite whatever property. It's finite. So it's very natural that the solution to your integral equation should also have a finite norm. And for that to be true, there's a condition on the right-hand side coefficients. Remember that those coefficients there to the right-hand side, which are at the enumerator right there, okay, for this sum here to be finite, okay, look at these, the squared numbers there must decay fast enough to 0. Okay, otherwise, if they don't do that, the sum is not finite, so they have to decay fast enough. Right? And we already know that the singular values decay. And we can say something about the decay of those guys depending on the problem we are solving. So what this is, that if we if we want to solve a problem, then the right-hand side, G, must have coefficients that decay even faster than the singular values, because otherwise the sum there would not be finite. Right? Oh. So that's very, very, very important to understand, that your right-hand side coefficients in this basis of the u functions, those coefficients must decay somewhat faster than the singular values. Otherwise, we cannot solve the problem. Otherwise, we'll have a solution with infinite norm, and we don't want that. Okay. So that's the Picard condition. I think this will be, of course, much clearer to you guys once we start to do numerical computations. But this is where it comes from. You sometimes see people say that, refer to this as a range condition. Sometimes you hear that expression, and it's the same thing. I just wrote it out here as the Picard condition. And certainly, a real difficulty here, when we solve real-world problems, is that the function g comes from measurements. We go out there in the lab, we do some measurements that represent our g. And so there's an exact component, the one we really wanted to compute, and then there's some noise on top of that. And the noise component, of course, doesn't know about the Picard condition, so it doesn't satisfy that Picard condition. So actually for noisy data, you can rarely compute a solution. And that's why we need all these stabilization methods that we're going to talk about in this course here. Right? Okay, so just a few more slides, and then we'll be done, because here's actually an illustration of the Picard condition for a particular integral equation where I could do numerical computations. Right. Let's see. There's a lot of stuff here, isn't there? Okay, let's look at the the top left plot right here. What do we have here? The blue solid line here, that's the true solution. The dashed green line, that's the right-hand side of my integral equation. Now let's look at the middle plot here. These are the various quantities that appear in our analysis if we do the singular value expansion analysis. And this is for a case where there's no noise in our right-hand side. Okay, so we need to look at the singular values, the coefficients of the right-hand side in the u basis, and then if we divide with the singular values, we have the coefficients to the solution. Let me just back up a little bit. These are the ingredients of the equation right there at the bottom. So these are the ones we want to know what happens. Right, here we go again. Right. Okay, so let's see. We have the red circles. Those are the singular values. And sure enough, they decay. And they must decay because we have defined them to behave like that. And actually, you can see how fast they decay if you want to do that. All right, so sure enough. And then the green crosses, those are the coefficients of the right-hand side in terms of the u functions. So they also decay. And sure enough, as expected, they decay faster than the singular values. All right, because you can see the slope is steeper. So it's not a matter whether the crosses are above or below the circles. It's the slope, it's the decay rate that's important here. And sure enough, they do decay faster than the singular values. So the Picard condition seems to be satisfied. The blue diamonds then are the ratios between those two quantities. Those are actually the coefficients of the solution in the v basis. And you see that they decay, so everything is all right there. Except when we start to add noise to our data. And I did that. I added just a little tiny bit of noise to my right-hand side in the discretized problem. And then I have the behavior that you see over here on the right plot. Okay, so apparently nothing happened to my singular values. Is that reasonable? That nothing happened to the singular values? Yes, of course, because I added a perturbation to my right-hand side. The singular values are entirely connected to the matrix, so nothing happens with the singular values, of course. Okay, but you see, now the behavior of the green crosses, the coefficients of the right-hand side, behave quite differently. At a certain point, you see they, instead of keep decaying, they level off at actually the level of the noise that I added in my right-hand side. And from there you can see that I probably added noise of the order 10 to the minus 5, 10 to the minus 6, something like that to my right-hand side. So it's tiny, it's a tiny bit of noise actually, but you can see it manifest itself right there. So from a certain point on, the right-hand side coefficients do not decay faster than the singular values. In fact, they don't decay at all. They seem to level off at a plateau. Damn it. And then, of course, my solution coefficients, which are the green crosses divided by the red circles, from that same point they will start to increase, because now we have something constant divided by something that keeps decaying, and so you're going to have solution coefficients that increase from that point on. And if we go on, you will see them ever increasing towards infinity. Right, so what you see right there is that the solution consists of all those coefficients corresponding to the blue diamonds, and you see some of those coefficients there from I greater than maybe 20 are completely determined by noise. They're just noise divided by small singular values. And those coefficients are of the same size as the good coefficients there you have for small values of I. So our solution is completely destroyed by the influence of the noise right there. Right. This gives us actually an idea what to do in order to compute a more stable solution. We should try to do something about those noisy coefficients of the right-hand side. And that is the philosophy actually behind the regularization methods that we'll talk about in a few weeks from now. Okay? But you see, all those difficulties that we encounter when we solve the problem on a computer can be related to something very, very fundamental about the integral equation itself, and we can express that in terms of the singular value expansion. Right, we can do the singular value analysis, and once we have done that, we can plot these quantities here. That's what I call a Picard plot. Give us a lot of insight into what is going on here, how fast do the singular values decay, so on and so forth, where does the noise set in, and give us an idea what to do, get rid of some of the noise coefficients there, and from there we will arrive at actually computational algorithms we can use to solve the problem. So this is an important thing to remember here about the singular value expansion. Okay, 3 more slides to go. I do want to show you this example here. This is an example of an integral equation that doesn't have a square integrable solution. So it doesn't have a solution with a finite norm. I just want to show it to you. It looks so innocent, doesn't it? But apparently this particular solution, look, the right-hand side is just a constant 1. And that right-hand side does not satisfy the Picard condition. Right. I'm not going to go through all the details here. I just want to show you that if you compute these partial sums related to the singular value expansion, you will obtain a sequence of functions that does not converge. And if you really want to dig into this, you can read this in the book, because it is quite fascinating. Here you see what happens when the Picard condition is not satisfied. So these are just partial sums associated with the singular value expansion. And if you look at the ordinate axis, you will see that these functions there just get larger and larger, and they are larger nothing. It refuses to converge to anything. So it's just an example of something that looks very, very nice and innocent, can actually be really, really impossible to solve. Anyway, my last slide here is that we basically motivating that we need to spend the rest of the course on numerical methods for doing this, because although the singular value expansion is pretty amazing because it allows us to obtain so much insight about the underlying problem. Unfortunately, there are very, very few practical problems for which you can actually write down in analytical form the singular value expansion. So that's unfortunate. One of the important cases where you can do it is actually the radon transform that is sort of behind X-ray computed tomography. So that's a nice example. And a few other examples. But really, for most of the other problems you encounter in practice, you cannot write down the singular value expansion. And that certainly calls for numerical methods. So we can do the same kind of analysis here, but now with matrices and vectors that we have on the computer. Right. But we shouldn't forget that whatever we do on the computer, whatever we compute with our data, should reflect this analysis here that we would really like to do in terms of the singular value expansion. So that will be the starting point for the lectures next week. Okay, so I'm done for today. Right. So we stop here. Yeah?